Welcome to this third and final recorded video for the Part A lecture notebook for the third module in this course. So this discusses something that can seem rather subtle at first, and it might take, I kind of jokingly say here, perhaps 10 times to work through this. Hopefully not that many, but it's probably worth reading through at least twice. And the topic here is pass by reference, pass by value, in-place operators, and we also talk about the scope of variables with respect to functions. So there is very little substitute for just taking some time and patience and learning this correctly. Here we seek to build just some basic intuition about what is going on so that you can be aware of some potential pitfalls. There's also a link here that I think is a good place to start and read some other people's perspective on this, but we're just going to kind of dive right into this, which is to start with a metaphor. How would I describe pass by value in more layman terms? I would describe it in terms of passing information on pieces of paper. So pass by value would be where I have perhaps information written on my piece of paper, and you're the function that I want to operate on my piece of information. But if I'm doing a pass by value, what I would do is copy my information onto a new piece of paper and hand you the copy. Maybe I give you the information that x equals 5. This is now a copy of paper that you have, and you can do whatever you want on that paper. Maybe you multiply x by 2, and maybe you just decide to erase that x equals 5 on your piece of paper and make x equals 10. Now you return that piece of paper to me. Does this change what was written on my original piece of paper? Of course not. It's up to me whether I want to use that information at x equals 10 and change anything on my piece of paper based on what is written on your piece of paper. This is what your function has returned to me, but it hasn't changed the value of x on my piece of paper. It's up to me to decide if I want to do that or not. Pass by reference basically says, I just give you my original paper. Now x is equal to 5, and you might again say, I'm going to erase and replace that x equals 5 with x equals 10. And then you give me that original piece of paper back. X is changed regardless if I wanted it to change or not. The choice has been made for me by you that x is equal to 10. I sure hope that's what I wanted, because that's what happened. So the main idea here is that if you don't want values to change without your consent effectively, then you want to pass them by value, not pass by reference. This is also, so in a more technical sense, this is what's going on. When you do pass by value, Python creates a new copy of the variable within the function. So you can think of that in the metaphor as a new piece of paper is created, a copy, which is used to track the variable information, but the original variable information, because it's on a different piece of paper, is not necessarily changed. This happens automatically with variables of certain type that are passed as parameters to functions. Strings, floats, and ints are all immutable data types. So they are unchanged by a function value. They are passed, or by a function operation, they are passed by value. Pass by reference means that Python passes the memory address, the location where the variable is stored in the computer. In terms of the metaphor, this means the original piece of paper is passed to the function. So this can cause some very different behavior when certain in-place operators are used, and we'll see examples of what in-place operators are below. Classes, list, NumPy arrays, things of that nature are mutable data types, and they are passed by reference by default. So if you don't want the actual class, list, or NumPy to change on the, let's say, original piece of paper, what you really need to be careful about is using in-place operators, which have their place, not to be punny here, but they have their place. However, you want to just be careful about when you're using them. And so we have some activities that get to the heart of that. Now, this leads us to discuss what is this thing called scope. Python variables created within a function have what is called local scope. Scope usually refers to the visibility of variables. In other words, which parts of your program can see or use it. We saw examples of this above. Local scope usually means only the called function knows about these variables created within it. Like, when I'll just scroll up above here, this variable z that's created within these functions, unless we assign z equals to whatever this output is, Outside of this function, nothing else knows of the variable z because it only exists and is created within this function unless we assign a variable called z equal to whatever is returned after the function is evaluated. So that was the example we saw before. And this gets into scope test. And within the scope test, we also study things involving the in-place operators. So let's look. This is an example of an in-place operator. In this first scope test, we pass a variable to it that we call var, and we print what that variable is passed to scope test. Then what we do is we take that variable and we multiply it by 2. This is an in-place operator. This is like the same thing, kind of arithmetically, it looks like this. Var equals var times 2. And it's a shorthand for that computation. But what we're doing is using an in-place operator. So what will happen is if var is mutable, meaning it's like a NumPy array, or a list or a class, then this will actually change what the variable var is outside of this function. Even though notice we return nothing from this function, var will still change. Now here's something else that we do. Within the scope test, we after that we show what we did with var. And var will be changed within this function. If it's an immutable type, meaning it's like an int, float, or string, this will be different here, but it will remain the same outside of the function. If it's mutable, what it's changed here will also change it outside, if it's mutable, it will change here and outside of the function. The examples make sense. You have to go through this probably a couple times, like I said. Now here's a variable that's created entirely within the function. It doesn't matter, as you'll see, that we create a variable called a that is not 3, like we make a equal 2 here, outside of this function, and then we show, hey, here's what a is inside of this function. We made a variable called a, but then we'll check, did that change what a was outside of this function? Let's go through some examples to make this more concrete. So we have now defined the function. Now here I make an immutable data type in integer. I pass a to scope test. It is now called var as far as scope test is concerned. I do this operation here. I will print what it is. I will define a with inside of this function to be something different than 2. And then I return nothing, and I will see what does a look like at the end. So let's look at all the print statements that occur from running this. So a is 2. Before we run that function, a is 2. We pass it to the scope test, and it's called var inside of scope test. That's what the parameter is called. So there's the value of 2. Within scope test, we take that var and we multiply it by 2. So it becomes 4. Within scope test, we take this variable a and define it to be 3. So here is a equals 3. We then leave this function, we return nothing, and we investigate what was the value of a after all of that. It is still 2. Let's look at what happens when we make a to be a mutable type. So here is an array that is just 2 and 2. In fact, we'll just run this. Excuse me, it's a 2 by 2. Excuse me, it's a ones. I was looking at that and I knew I said it wrong as soon as I said it. This is an array of ones that is of size 2 by 2. So it's a 2-dimensional array, a 2 by 2 array, and it has entries of all ones. So here it is. It is then passed as var 1, 1, 1, 1. There it is inside of the scope test. We then do the in-place operator to multiply it by 2. Here's the output of that, 2, 2, 2, 2. Now we made a 3 within scope test. After scope test, look at what a is. It's 2, 2, 2, 2. It's what happened here because a was passed as var here, and we used this in-place operator. It was passed by reference, and it changed what a was. It didn't matter that we then called a equals 3 because var is really the variable a in this. Again, you might want to go through this a couple times. It can be confusing before you get a handle on what the role of a is and what var is with relationship to a in these functions. So now here's something even a little different. We'll make a to be a 2 by 2 array of ones. Again, we will define b to be 2 times a. So now what we do is before the scope test, we change what A is, or excuse me, yeah, we let's just run this. I don't want to say something incorrect. So here is the scope test. There's A. Before scope test, there's A. And then the variable passed to the scope test, though, is B, which is 2 times A. So that's a 2, 2, 2, 2. Right? We just multiplied. It's an element-wise operation. So all the ones got multiplied by 2. Within scope test, it's now 4, 4, 4, 4 after we do the in-place operation. So did that change B or A or both? Let's see. So after scope test, if we the scope test of 2 times A, really I should say it's B. After scope test B, let's look at what A is. So there's that variable 3 again. That doesn't matter at all. So I'm going to rerun that so that it's printed right. After scope test of B, A remains unchanged. It's still all 1s. B was changed to all 4s because this was what B was. B was 2, 2, 2, 2. Then it became 4, 4, 4, 4. So again, it might take a little while and a few times of going through that before it starts to make sense. And it doesn't have to make perfect sense. You just want to be aware of what this in-place operator is doing more than anything. But I do recommend going through that 2 or 3 times. So if you look at that and say, look, this is maybe problematic. I don't like that my mutable data types like a NumPy array are changing based on what's going on in the function. So how do I fix that? The answer is to not use an in-place operator like plus equals, which will take a variable and add to it whatever you write on the right of it. Divide equal, similar thing with division, times equal, like we saw above. These are what are called in-place operators. So instead, if I had used var equals var times 2, and I just made a simpler function, which I call scope test 2, here I have var equals var times 2. This now will create a local copy of var. So even though it's passed by reference, this then does a copy operation, and so it's no longer doing it no longer replaces the variable value in place. So here, I'll make A to be a 3x3 identity matrix. So you'll see here, there it is, 1 0 0 0 1 0 0 0 1, and then I do this times 2, but I don't do times equal to. I say var times 2, and that var definitely got changed inside the function. I return nothing. Did A change? No, it's not 2 0 0 0 2 0 0 0 2. That would be what happens. You can go and try this. If I made this times equal to. See, now it is 2 2 2 on the diagonal. So I will switch that back, and that's the advantage of not using an in-place operator if I didn't want A to change outside of the function. I just wanted to operate things on here and return or not return anything and make my decision about what I do with the output of the function rather than having that decision made for me. So I have some other tests here. I'm not going to run through them in the interest of time, but I'm going to go into this instructor-led activity, which, if you look, has a lot of instructions, but it's really just setting up a problem, and it's very much related to what I ask you to do with investment functions. So here, we'll go read through this, and then I'll show you the amount of code you have to do, which is not much for an activity like this. You might even want to try to pause this video now, work through this activity in 5 to 10 minutes, and if you get stuck, come back and watch the video. If you finish it, come back and watch the video and see if you got what I got. All right. The simplest formula for the height of a falling object under the influence of gravity and dropped from an initial height is given by h of t equals h of 0 minus 1/2 gt squared. Here, h of t equals the final height of the object at time t. H of 0 is the initial height of the object when it is dropped at time 0. G is a gravitational constant. On Earth, this is approximately 32 feet per second squared, or 9.8 meters per second squared, depending on what your units are. And t is just the total amount of time the object has been falling. And if we're using units of gravity like this would be in units of seconds. So this is a crude model, of course, because it assumes the object falls in a vacuum, there's air resistance is neglected, and h of t can be negative if we choose t large enough, which perhaps is kind of silly. Despite these crude aspects, we are going to use this formula to estimate the final heights for some objects falling over various amounts of time while subject to different gravitational constants and dropped from different heights. However, we have two separate objectives. One is to predict the estimated distance traveled for objects that are not yet falling, while the other objective is to update the distance traveled for objects that are already falling. So we will create two functions for this purpose. One is predict distance, and the other one is update distance. Notice the underscore there. You can't do separate words. You can't have a space in your function name. These perform element-wise operations on NumPy arrays of h, g, and t values. We want to use an in-place operator to update the array of h values in the update distance function. So let's just go ahead and look at the structure of this initially. I want to have a predict distance function, and it's going to have h, g, and t as parameters. I'm going to have a update distance function, and it's going to have h, g, and t as parameters. And the question is, what goes into this? So I might say, look, h is equal to this, h minus 1/2 gt squared. So I'll say h is equal to h minus 0.5 times g times t squared. Whereas here, I will have h minus equal 0.5 times g times t squared. Because I'm updating the distance, I'm going to use the in-place operator. Here, I return h. Here, I don't have to return anything. So I could just, if you'd like to have return with nothing, that's fine. In this case, if you're returning nothing, you don't even need a return statement. But we'll write it there just so you can see that we're not even returning anything. So here I return h. Here I return nothing. Those are my two functions. That's as much code as you have to write. So I know there's a lot of text here, but there's actually not much code to write. You just have to read the text carefully. Now, let's say that I create an array, and I'm going to do something at first to give an error that is related to what I describe an error that you might get down here. So we'll just see it as a second. So imagine I make h as an array, and I say, okay, I'm going to have something drop from 100 meters, 200 meters, and 300 meters. And I'm going to have gravity constants of, let's say, 9.8, and then I'm going to, let's maybe half it, 4.9, and then, I don't know, 10. So it depends, maybe you're different places on Earth, or you're somewhat in outer space or on the moon, and the gravity constants are changing. We're just trying different gravity. The arrays just have to be the same shape in order for things to work correctly. And then we'll look at some time values, let's say 5 seconds, let's say 10 seconds, and let's say 7 seconds. So we'll run that there. Now, look at what happens when I print predict distance hgt. I produce the predicted distances, and notice some of the values are negative, like I said could happen. So something dropped from 100 meters with a gravitational constant of 9.8 meters per second over 5 seconds will be at negative 22.5 meters. So it's gone 122.5 meters down from the 100. So that's why it's the negative value. And then there's these other values. Notice they're floats. They are floats. Now, I did not use an in-place operator here, but I'm returning h. Let's look at what h is. It is still 100, 200, and 300. I am not using an in-place operator. Now let's look what happens when I run update distance on h, g, and t. And I'll go ahead and try to print this. Now this should produce an error. A function type error. What is going on? It's saying you cannot try to subtract output from a float type to an int type with your casting rule. They have to be the same kind. You have to try to make sense of that. What the hell does that mean? Just kind of like what I ask here. What the heck? Well, maybe I didn't say what the hell. What is going on? What happens here? All right. Think about what's going on. H, look at this as a data type. This is an array, in this case, of all integers. I didn't have to make them integers. I just happened to make them integers. And if you check the D type of that, if we look at this, print h dot D type. Oh, I'm sorry, that's an attribute, so I don't need a function there. Typos abound. That is an integer type. But as we see from the output of this operation, it will produce floats. So the problem is when the array has this the data type of it is integers, but I'm trying to change it to floats with an in-place operator, that is going to cause errors. So you say, oh, well, how do you get around that? You could come to here and say, this needs to be as type float. So now when I ran it, there's your 100 point, 200 point, 300 point. So it's the same values, but I'm making sure if I ever want to use them as in-place operators, this should work now. So now notice I'm printing the output of this function. It doesn't return anything. It's none. But let's look at H. Now it's changed. It's no longer 100, 200, 300 because I used an in-place operator. All right. So that's one way that you can handle this type of error if you come across it, is you could say, look, I want to handle this as a certain type here. There's perhaps other ways for you to try to handle it, but I just point out this is related to something you might do in this investment function, which you should read carefully. It's similar in its operations. You are either trying to update or project a balance, and where you use an in-place operator on the update balance, if you have principal amounts that are all integers, you might encounter the same type of error. And I'm explaining how you can deal with it by making sure that your arrays are of the right type. So that's really it for this lecture. I want you to try this one on your own now, but I'm free to answer questions of that in office hours or on the discussion boards on Canvas. After that activity, the last thing for you to do is the summary. So that's it. Thanks for listening, and I'll be talking to you in the videos for the Part B and Part C lecture notebooks for this third module.